But now I am. Awesome. So hello everyone. I don't know if you guys can see me, but I think you can hear. And that's all I need. So today I'm going to be working with my boy Steven. Right here. Don't think this and I can only see what I have in my tablet, but that's okay. Get through this. Okay. So I have the page to this blank.
Because the problem was kind of like the fluid through a cylinder with a catheter, but it was essentially
so we have a cylinder, and then we have a smaller cylinder. Awesome. Okay.
And then the fluid is like on the outer cylinder is going left.
It's going left, from right to left. Like
from right to left, yeah. And
okay,
then
so this liquid is going right to left.
And then from like in the smaller one, it's going from left to right.
When you say the smaller one, you mean the catheter?
Like the catheter, yeah.
Oh, okay. So a catheter is going this way. Okay. So we have this. So it's a cylinder. Awesome. Okay. This cap. Okay.
And so I think I use like Navier-Stokes for like an incompressible fluid.
What were the assumptions? Was that Newtonian?
I think it was Newtonian, no gravity.
Okay. Yes. So okay, so assumptions were Newtonian, no gravity,
steady state.
Steady state. What else?
And then velocity was only a function, or like velocity was only in the z direction.
Velocity. So velocity in the if we define our catheter to be C R, and then I don't want to state that we already care about. Velocity in the z direction was only a function of r, right?
Yeah.
Okay. Okay. That's what we got.
Mm-hmm.
Okay. So, okay, let me look for the Navier-Stokes equation really quick. Do you have it by any chance?
Yeah.
Okay.
So I think
I'll take a picture of it really quick. Oh, I can see. Okay, I can see it. I'm not. Okay, it's Navier-Stokes. Awesome. All right, so this Navier-Stokes. Okay, so tell me what you did.
Essentially, you can cancel out like dvz over dt.
Okay, why?
Like it's steady state.
Okay, awesome. Because of steady state. Okay, what else?
There's no VR.
Are we in what direction first? I think we jumped that. What direction is the flow?
It's in the z and also like negative z.
Okay. Okay.
So,
hey, that's a good catch. Yeah, because you have the velocity going in one way, and the velocity. Oh, so in this case, if you define the liquid being positive, then your coordinate system has to go to the left. Your z direction. So we have to make that arrangement. So the liquid is going to be positive, while the cat is going to be negative, based on our coordinate system, right? Okay, let's keep going. So you said that in accumulation, yes, the z is not a function of x.
I say like
Go ahead.
that it wouldn't be.
I was, please. There you go.
So there's no V theta, so you can take it out. There's no VR.
So we are, yeah. So we
And
are.
then VZ, your velocity is a function of
theta.
R, not Z. So you can
Okay,
also
so we
cancel that
can
out.
so we can cancel all the left
Yeah.
side.
And
So
then
left. Yeah, awesome.
and then there is like a density
Okay,
gradient, so you can keep that
density. Oh, this with where?
like or pressure, sorry.
Oh yeah, the pressure on the other side. Yeah.
And then
So the liquid is pressure driven. Okay, that's good. You know what that means? What delta P
over DZ or delta
P
Z.
over L. Do you know where how that negative delta P over L? You know that one how that one works? How
Yeah.
yeah. How does it work?
Essentially, like your change in pressure is a function of your length.
Yes. And that one is equal to our term, like our which term?
What do you mean?
Like in our Navier-Stokes equation, if I were to like substitute this value, where would I put it?
Like what do you, like here or like your dp over
Yeah.
wouldn't it just be your change in pressure over DZ or delta Z? Oh,
Yeah.
okay.
That term is gonna be equal to that.
dp over L, yeah.
Yeah. All right.
And then you can cancel like
So
the last term because there's no gravity.
okay. We can cancel the last term. No gravity. Yes. No gravity. Do we have VC over Z? Like, is that a thing?
I don't think so
Okay.
because it's a function of R, not Z.
Correct.
And then it's not a function of theta, so you can cancel that one out, and so you just
Awesome.
get the first term
First
essentially.
term. Okay. So we get 0 delta P over delta C plus mu 1 over R. And then we have the partial with respect to R of R VC R. Yeah. Okay. This negative. Great. What do we do now?
I don't know, you can set them equal to each other, and they're equal to like a constant, so C1.
Yep.
So then you can just integrate for them.
And do you know what the constant is equal to?
I know, like since we derived it before, you can just use it.
Yeah.
I think, but I don't remember it.
We have it in the assumptions.
What do you mean?
This guy.
Oh, okay.
Since our right side in this case is equal to delta P over Z, and that we know that delta P over Z is negative P over L. We know that C1, it would then be equal to negative delta P over L. Great. What do we do now?
And then like I get confused because can't you just solve for like when you have 1 over R and then you have like another R, won't they just cancel out?
No, because
they're like different functions.
You are taking the derivative of what is inside.
Oh, okay.
So you're taking the derivative of the first one times the second one plus the derivative of the second one times the first one.
Okay.
And then you're distributing the R. So then you can subtract by R.
Okay.
Not necessarily.
Not before.
Not before. Yeah, that's not. Yeah. What you can do though is pass it to the other side. That will take the form of negative delta P over, well, negative delta P over L mu, and you're multiplying all of that by R, right?
Mhm.
And then we get, that's going to be equal to the partial R over dVz dr. Awesome. So we can integrate now. No, doesn't want to.
Oh, okay, that's what I wrote.
So you wrote that. Awesome. So we can then take the integral. Yeah. So with respect to R on both sides. Well, with respect to R in the left side, so it will be negative delta P R over L mu dr. Now we can use like definite integrals because we are, I mean, not partial, but a normal d because we are not considering other variables. So we can use the r, and then on this side is the derivative of this. So essentially we cancel the derivative with the integration, and this side what would we get?
D R squared over
Mhm.
2 L times mu.
Is that only that?
And then plus constant.
Yep. On the other side we get r.
dV over dr.
That's right. So now we can cancel r.
Okay.
So now what you can do is divide everything by r. So you're gonna get delta P R in the left side, 2L mu plus C2 divided by R, which is equal to dVc dr. Okay, what else?
And then you essentially multiply by dr on the other side, and then
That's
integrate.
right. It's negative PR over L mu plus C2 over R. dr is equal to dVz. We take integrate both sides. And then we get negative PR 2L mu plus C2. Whoa. What do we get? I almost wrote the same thing.
You get negative delta P times R squared
Yes.
over 4
Yes.
L times mu, and then
Correct.
plus the natural log
That's right.
of R, or
Mm-hmm.
and then I always forget, like, when you have is it C2 times the natural log of R?
Mhm.
Okay. Equal.
Mm-mm. They're forgetting somebody.
Plus the constant.
That's right. Okay, so we have our general solution for velocity.
Okay.
Solution. Copy fix. Okay. I'm gonna change to black right now. So what do we do now? So we know this expression, and we have some assumptions at the beginning, right? What can we do? Also, we could derive some boundary conditions. That's something that I remember that you talked about.
That's where I always get confused,
Not a
because
problem.
I don't know, like, I know the boundary conditions, like your velocity is going to be 0 like at your edges, and then in the middle it's going to be max, and then your shear stress in the middle is 0, and then at the edges it's like your max.
Yeah, but you have to be careful in this case because the liquid profile is different.
Okay.
So different that I wouldn't really know how to write it because the catheter in this case is not static.
That's why,
It's like moving. So you know that liquid is going that way. It's going to the left side. But also the catheter is moving to the right side. And you know exactly what the velocity is. So you can approximate that it's something like that. If you're assuming that the catheter is going slower than the blood. So that you have, in this case, you have flow going this way and then flowing that way. Kind of. This is just us assuming. Maybe the catheter is going so slow in comparison to the actual flow that is minimal. But some flow should go backwards or try to go backwards. And maybe this is so maximum that it's not really going backwards. Like the difference is like to the left side.
Okay.
Or it could be the difference to the right side, but that's very rapid and not necessarily. Yeah.
I think like the way I read the problem, I like just assumed it was like static essentially, and just like there was fluid inside the catheter, not like the catheter was moving. But that probably was wrong. I don't know.
Interesting. Well, what do you think?
Well, because it said like primarily it said that there was fluid inside the catheter moving, not that the catheter itself was like.
Oh wow. That
Or
for sure.
maybe
That for sure changes things.
I probably read it wrong. I don't think I did too hard on that one.
Do you get your exam today?
I got the exam 1 and I did fine on that one, but
Oh, okay.
exam 2.
It's not this one. You're gonna pick one?
Hmm?
I mean, since we don't have the problem.
Okay, yeah. We can just keep on solving for this one.
Okay. So we're assuming that the catheter is moving.
Yeah.
Okay. It's really a big difference. I mean, if you remain consistent, it doesn't really matter. You're gonna get a completely different answer, but respect to, I think my intuition tells me will be the catheter, because in that case, it's not as easy. Because at that point, your Bmax is not necessarily in the center, and the velocity at the edge is not necessarily zero, at least for this velocities over here.
Moving, not the catheter itself.
No, the catheter itself. If the fluid inside was moving, you will only get this.
Or actually the opposite way.
Yeah. Yeah. That's what you got. Yeah.
So I just assumed that like it was like R, like that, like it would be 0, 0, and then 0 at these points, like your velocity, and then in the middle. So like 0, and then like it was like
Bmax.
R. It would be Vmax, yeah.
Which one would you like to solve?
Probably the easier one.
Okay. Well, that one. Okay, in that case, we know. And what would be calculating for? That's the only issue, because in that case, you're having two different systems. One that, so when you find velocity, you're gonna get a velocity for the one that is going to the left and the one that is going to the right. So you're not getting a velocity formula. You're getting two velocity formulas.
That was the issue that I was getting, because like I don't know. I think it might have just been straightforward. We have to like calculate just like fluid flowing like right, like fluid through a cylinder. And that would have been like your regular like equation, and then your fluid going left, and then imagining that there was like a catheter in the middle. So it would have been like that plus your middle one would have been like your total velocity equation. But I don't know if that was like the right way to say it.
You're saying that you have theoretically the velocity equation. You would first calculate this guy, and calculate this guy, and the difference will be your velocity of what?
Like the whole like the mass,
Of the entire mass
like your whole like
passing
velocity flow
through. Okay.
inside like the system
So
itself.
system.
Because you essentially have like two systems, like the outer cylinder and the inner cylinder. So if you just add them, that's your like total.
Would be the catheter mode. Yeah, because at that point, what I feel is that you're having two systems, which are different. I don't really see how you could integrate them unless you know where the catheter is like pushing whatever liquid it has. Because what you have in the cylinder is like blood. And the catheter probably you have is a drug or saline, which it's a valid example, but I don't know how to, like, you won't get a question like that in this class. Like having two different fluids in the same system and figure out the overall velocity now. Because also something that you guys haven't seen either. You always are working with one liquid and stuff happening to that liquid, like plates going on, like pressure, different geometries, like it maybe like the cylinder expands or contracts, or the area that he talked about. But I don't know if you put it on another thing from what you're saying, not that the area is irregular. So in order to calculate the area, it's like, and for the Reynolds number, it's like 4 times the area divided by 2 times the perimeter or something like that for the length.
You know, for like then this problem if it was a two system.
Yeah, I feel that's not the right approach.
Because I don't know, the way I read it was like it was like an outer cylinder and then inner cylinder, and there was like fluid going like right and then fluid going left because it was like a heat exchange thing.
Oh, okay.
So that's why like
okay, it was a heat exchange. Okay, and what was the question exactly? Remember?
It was essentially it was derive like your general solution for your velocity and your shear stress. Then part B was like establish boundary conditions.
Velocity and shear stress. Okay.
And then
So in that case, is what you're saying. If that's what the answer said, that's what, like, you're correct. Kind of weird though, but yeah. Okay, let's work with it.
I have to go.
We have to go
at like 3.
Oh.
It'd be fine if I like kind of like solve this and then send you like a group me thing or like a message so you can like check it.
If you can do, if I don't answer you within a day, please send me more stuff because I tend to just, I have a lot of stuff and tend to forget, but you can, if I don't respond, email me or stuff because this is something that, you do need to, like go over, like know where you will need to improve, or if you are good, like be confident that whatever you're solving, it's a good foundation so you can move on in the class for sure. All right.
I did good on the first exam, but the second one, I guess I didn't have like the foundation, because like I got to the general solution, and then after that I got kind of confused with all like the different boundary conditions for like your outer cylinder and your inner cylinder.
Hmm.
So